Hi, everyone. Welcome to our webinar on data center distribution using STSs. We're thrilled you joined us today to discuss this critical topic. The agenda today is as follows. We will begin with an overview of the benefits of STSs. From there, we'll discover data center architecture, where we will then take a closer look at the catcher architecture. Finally, we will wrap up with a discussion on the Socomec solution. We will have time at the end to also answer any questions you have. I now want to introduce our host and expert for today, Pierre Mira. Pierre has several years of experience in the data center industry and is a specialist in static transfer systems. Please join me in welcoming Pierre.
Thank you, Rachel. Hi, everyone, and welcome for this webinar. Today, I'm very happy to do this introduction on static transfer switches. And so let's begin. So to begin this webinar, we want to speak about the STS benefits. So how does STS improve your data center architecture? To speak about this topic, let's introduce the question, why a STS in an installation? So first, the difference between an ATS, automatic transfer switch, and an STS, static transfer switch. An ATS, as you are seeing on the slide, is upstream of the installation. It's connected between utility and genset in order to ensure the power to all the installation. So when you are losing your utility, the ATS will transfer to the genset for the genset to provide energy to all the installation. An automatic transfer switch usually has a transfer time of 300 milliseconds in the best case scenario, and also it will let the genset to ramp up, taking few seconds. In order to back up the energy during this transfer time and the genset ramp up, we have UPS in the installation. So the battery inside the UPS will provide the power during the few seconds of downtime. However, below this UPS, you should have static transfer switch. Why? Because if you have a UPS outage, the static transfer switch will be able to provide a transfer from the UPS A to the UPS B in 16 milliseconds in one cycle. So we speak about ATSM requirements. Usually in data center, we have the servers. Servers must be ATSM compliant, which means that they can accept a downtime of 20 milliseconds. So within 20 milliseconds, you must have a transfer from UPS A and UPS B. That's the STS, which is connected between the two outputs of the UPS. The STS will provide this very fast transfer. We can speak about 5 milliseconds with a fast transfer option. So STS will provide this very fast transfer between UPS A and UPS B. While if you were using an ATS, the automatic transfer switch, with a mechanical transfer, it will be 300 milliseconds. So the ATS is not the right product for this application. When you speak about ATSM requirements, we must use static transfer switch in order to provide a very fast transfer. So let's continue about why a STS in the architecture. So now in 2024, most of the data centers, they are using dual coded servers. And so we have a lot of time the question of why still using static transfer switch when we already have dual coded servers. To answer at this question, and the first question is related to the upstream protection. So here is our example on the left about load, which are powered by PDUs, dual coded load powered by PDUs, and each PDU is related to a UPS. At this moment, we can simulate a failure on a UPS. So a failure can be a water leakage, a fire, a cable destruction, a breaker tripping, or on the UPS, a human error. It can happen, and when it happens, we must anticipate this failure. In the case of you don't have a static transfer switch, what will happen is you will lose your UPS, And at this moment, the UPS will not be able to power the PDUs downstream. So your PDUs will be off. You will not have any more power on your PDUs. And the load, which must be powered on the secondary side, on the path B side by the PDU, will not be powered. So the load, being the servers, will have an alarm, and the customer using the load will be notified that there is an issue in the architecture. There is a fault, and the load gets an alarm because of this fault. So the server has an alarm because we lost the PDU. And why did we lose the PDU? Because we lost the UPS. The second kind of architecture is the same using static transfer switch system. Now, when we have a static transfer switch system securing the PDUs, we can still simulate the UPS failure, same kind of failure. And what's happening if you are losing your UPS upstream is each STS will detect the UPS failure. All of the STS which are powering the load from UPS B as a main will be able to transfer their load. And so at this moment, you see the PDUs in blue, which will be powered by the UPS A. And so every single PDU is not affected by this UPS failure because there was a transfer. And so at this moment, the servers will not even detect the failure on UPS B. So it's a big advantage for your load, your server, to be blind from any UPS error. Of course, there will be a report on the UPS and on the static transfer switch. Static transfer switch, thanks to waveform capture, will be able to see the timeline on when the error happened, but will still manage all of the power upstream in order to have very safe PDUs providing power to the load. So when we have any upstream event on the UPS, on the switchboard, the static transfer switch is securing every single load below it. The second question related to dual coordinate servers is how do we secure our load from downstream events? So here again, on the left side, we have the data center architecture without any static transfer switch. If we simulate a fault on a PDU, what will happen? We lose the PDU. The server, the load which are connected to this PDU gets an alarm. We don't lose the server because they are dual coded. However, the server gets an alarm, customer is notified. So at this moment, the fault will propagate up to the switchboard and up to the UPS. On top of that, if the breaker don't trip on time, the fault will propagate up to all of the other PDUs connected to the same UPS. So we will lose all of the other PDUs connected, and the servers will get alarms. So again, it's not the safest installation. We don't lose our load, but if there is anything happening to one path of the server, we can lose the server. So bringing a STS in this installation will help us to be secure from any downstream event. Here is the example of how the STS will behave. So again, fault on the PDU. We lose the PDU, and the server connected to this PDU is not isolated from the PDU. So we get an alarm on this server, but only on one server. Because at this moment, the issue, the fault which should propagate, will indeed go up to the UPS, because the static transfer switch will detect that it is a downstream fault. So the STS will lock on the fault. It does lock on the fault in order to let the upstream protection trip. And we don't want to create some back and forth transfer to UPS A, UPS B, UPS A. So that's why the STS is locking on any downstream events. However, when the fault should propagate to the other PDUs. It will not happen because all the other static transfer switch will detect from their point of view it's an upstream event. So they will transfer to the safe UPS. So at this moment, all of the PDUs are fully secured and all the loads are fully secured. The customer is not notified that there is an alarm on the load. So it's another level of resiliency in the architecture using static transfer switch. We can call this advantage load segregation, load islanding, PDU islanding. And so that's showing that having a static transfer switch in our installation help us to secure our PDUs, indeed securing our loads. So small recap on why should we use static transfer switch to protect dual coordinate servers. First, to protect the load, the PDU and the load from any upstream events. So avoiding the risk of being one leg, being transparent from any upstream protection, and bringing redundancy closer to the load. The second advantage is the islanding of every single load. So every single downstream failure will be protected by the STS because every load will be islanded from the others. So now that we understood the advantages of bringing STSs in the data center, let's look through different data center architecture. So here is an example of a data center. We see the white space at the bottom of the slide. So the IT racks being the servers are in the white space connected to the PDUs fed from UPS. So here, the first data center architecture is called the 2N architecture. 2N because every time we have a UPS and a redundant UPS. So every load is secured by 2 UPS upstream. Here in this example, we look at IT load being 3 megawatts. So if we have 3 megawatt IT load, we will need 2 times 3 megawatt of UPS, a total of 6 megawatt of UPS, securing the load. At this moment, UPS are working at 50% of their nominal power, of their maximum power, feeding PDUs. What's happening, as we explained earlier, is if we lose one UPS, we lose the PDUs connected to this UPS, and the servers are getting alarms, customers are getting alarms from the servers. In order to increase the resiliency of this architecture, we can add static transfer switch. So at this moment, the static transfer switch will provide redundancy closer to the load. And in case we are losing one UPS, the static transfer switch will transfer the PDUs in order to feed 2 paths of the servers. So at this moment, on a 3 megawatts IT load architecture, we have to bring 7,200 amp of static transfer switch. Second architecture that we want to speak about today is called distributed redundancy. Here in this example, for distributed redundancy, we'll speak about 3N2 architecture. In North America, we can speak about 3 to make 2. Another kind of architecture for distributed redundancy would be 4N3, 4 to make 3, or 5 to make 4, etc., etc. So here in this example, to make it easier, we'll speak about 3 to make 2. When we have this 3 to make 2 architecture, we must size the UPS according to the IT load. If we have 3 megawatt of IT load, we'll have to size 1.5 times the power for this UPS. So for 3 megawatt of IT load, we need 4.5 megawatt of UPS. It's very important to understand that in order to do the right sizing of the UPS. In a distributed redundancy architecture, if we are losing one UPS, all the other UPS will be ramping up in order to manage the power sharing to the load. So at this moment, we don't lose the load. Again, we are in data center, so we must not lose the load. However, now load are exposed to second issue. if there is an issue on the coding of the servers, if the server see a fault coming from the PDU, the server will be affected by this issue. So bringing, again, static transfer switch in this architecture, in this distributed redundant architecture, help to enhance the resiliency in your data center. So again, we keep the same sizing of UPS, 3 megawatt of IT load, 4.5 megawatt of UPS, loaded at 66%. And now we bring 7,200 amp of static transfer switch in order to increase the redundancy of the data center. So if we lose a UPS, the STS will share the load in order to fully secure the servers from any power outage upstream, and also still bringing the safety from any downstream event. The last architecture for data center, which is very common in North America, is called block redundant or catcher architecture. The catcher architecture relies on a redundant block of UPS. So what we are seeing here is the catcher architecture only works with static transfer switch. Each static transfer switch is connected from the main side to UPS A, B, or C. It can increase with up to 6, 8, 10 UPS. And we have on the second input of the static transfer switch, the redundant block. So when we have the UPS failing, the redundant block will provide the power to all of the static transfer switch which were connected to the failed UPS. So in this architecture, when we have 3 megawatts of IT load, we only have to use 3 megawatts of UPS plus X amount of megawatt for the redundant block. I will not say one architecture is better than another one. It all depends on the power of the IT load. For example, if we are speaking about small number of megawatt for the IT load, maybe we don't need the catcher. It will depend of every single architecture, depending on how resilient the architecture should be, how much money we want to invest in the architecture. One architecture, we can save probably some money on the UPS, but we have to spend more money on efficiency of the architecture. We can save some money on the cabling on the breakers, depending on one architecture or not. And then it depends on the level of resiliency that we want to have from the IT level. So in a 2N architecture, we would load the UPS at 50%. In a 3N2 architecture, distributed redundancy, we would load the UPS at 66%. Another example is a 4N3 architecture at 75%. And in a catcher architecture, all UPS are working at 100%. And the block redundant UPS will be kicking in and replacing any failed UPS. So to do an exercise of sizing in an 18 megawatt data center, with a 2N architecture, we would have to get 36 megawatt of UPS. In a 3N2 architecture, we will use 27 megawatt of UPS. And in a catcher or block redundant architecture, we would have, in this case, 18 megawatt of UPS and, for example, 4 megawatt of UPS. So block redundant UPS can have different power level depending on the level of resiliency we want. I want to zoom in on the catcher architecture. So that's the next slides of this presentation. It's a zoom on the catcher architecture. Because in the previous slide, we saw that catcher architecture was with 2 STS connected to the servers. Here is an example of a catcher architecture with only 1 STS connected to one path of the servers. To do the exercise, we'll use a 2 megawatt UPS as the main, and the block redundant UPS will be 2 megawatt as well. There is several block in this architecture, 2 megawatts, and again, the block redundant is 2 megawatts. The example is using static transfer switch 800 amp, feeding PDUs, feeding servers. So in this case, the servers only have static transfer switch on their A path. The B path will be without static transfer switch, meaning if we lose the UPS, the A path will be fully secured by the static switch and the block redundant UPS. The B path will be left and the power will not be feeding the servers. So again, the servers will be detecting and getting an alarm. However, they are still safe. Some customers accept the server being on one leg. So that's an exercise of having a block redundant architecture, accepting one leg servers. The second architecture that we are seeing in the data center industry is catcher architecture with one STS, one ATS. In this case, STS is still connected to path A of the servers. However, the path B is powered through an ATS. It means that in this case, our customer, our server owner is accepting to have his path B getting a downtime of few milliseconds. Path A is fully secured through the static transfer switch and will maintain the high level of resiliency. And path B will be getting a small downtime because the automatic transfer switch will transfer, but taking more time than an automatic transfer switch. In this case, the two paths are secured. However, path B gets a little bit of downtime depending on the ATS. To have the best level of resiliency, that's what we saw earlier, is using two static transfer switch on A side of the server and B side of the servers. So in this case, if we lose the UPS, the block redundant UPS will kick in and provide the power to each load. And so the server will be fully secured through static transfer switch. We have to make sure that the transfer to the redundant path are limited in occurrence and in duration. So we have to monitor over the time all of the transfer to the UPSs and understand why there was a transfer and how to ensure to minimize this transfer to have the most resilient architecture. Now that we saw the different data center architecture using static transfer switch, I'd like to take a few minutes to speak about the Socomec solution. So Socomec became one player in North America for static transfer switch from 2019. We have a long experience in static transfer switch worldwide, and we came in the North American market through our integrable static transfer switch from 200 to 1200 amp. It's a very unique design, having this integrable power module, because we are the first in the North American market to bring a power module static transfer switch inside the data center industry. This power module is patented. It's a cold swap patent, showing that, again, it's a unique solution in North America. This cold plug design, cold pluggable design, cold plug patented design, shows that we have the fastest serviceability in the market through the safe maintainability. We'll show the advanced feature of maintainability in the next slide. Having this design also helps us to show our very high resiliency. So we can have short circuit rated up to 100 kiloamp. We will support that. So it's a very high robust and fault tolerant design, having all of the redundancy features needed in a STS. To have this very high level of resiliency, I'd like to speak about the redundancy. Some people think STS is a single point of failure. However, it's not. STS is the last design securing the PDU, which is securing the load. So it's very important to have a very high level of resiliency inside a static transfer switch. Here in this example, we show the resiliency being very high from the redundancy of the architecture. Every single critical component is redundant. To begin to show this redundancy, let's see the power supply redundancy. In the Socomec static transfer switch, there is triple redundancy on the power supply. So there is one power supply connected to source 1, one power supply connected to source 2, and one power supply connected to the output of the static transfer switch. What's happening is even if we are losing a power supply or a source, the STS is still fully capable of working, and there is still a dual redundancy even if there is an issue on one power supply. The STS can still fully work with only one power supply. Second, very high level of resiliency due to redundancy is DC power redundancy. So we have two DC boards in the static transfer switch. So it means that even if we have a DC board failing, the power coming from the source or the output will be distributed in DC from two DC boards. It's again another level of redundancy. What we have as well is the redundancy on the microcontroller. We have in the Socomec design, we have two microcontrollers on two independent daughter boards connected to a motherboard. So what's happening? Each microcontroller is fully autonomous, and each microcontroller is able to control the static transfer switch. It has all of the settings. It's recording all of the data and keeping all of the data. On top of that, each microcontroller, they are talking to each other in order to make sure the other one is working. So if we have a fault on one microcontroller, the second microcontroller will be able to manage the static transfer switch totally independently. Another advantage of the redundancy is to have redundancy on the SCR drive. So the driver boards are fully redundant. So on the path source 1 and on the path source 2, we have a main driver board and a redundant driver board. So even if we have any driver board failure, the STS is fully operating and fully distributing the power to the load. So if we have SCR driver failure, it's fully safe, we can still operate. That's something we can simulate. If someone is challenging us, we can do some simulation and show that the static transfer switch is fully working with any of these default being created. Static transfer switch has all of the control through the microcontroller, and these microcontrollers are independent, meaning it could be controlled from an HMI, but the HMI are independent, meaning if we lose the HMI, STS will fully work again. It can also be connected with output breaker. In the data center industry, in the specification, people are calling for redundant output breaker. Our static transfer switch are fully compliant with this standard. It can be connected with two output breaker, and it can monitor these two outputs. We are in North America working with PDUs. STS are connected upstream of PDUs. So it will initiate transfer on transformer being in the PDUs. When there is no specific algorithm, and when we do the transfer in 5 milliseconds on a PDU in a transformer, it will create an inrush. It's something that we don't want, and it's created by the transformer because a transformer has some magnetic flux, creating some inrush currents when there is a transfer very fast. So With a standard static transfer switch and a fast transfer, a transfer in 5 milliseconds on a PDU can generate an inrush current up to 10 times nominal current. We don't want that. So in Socomec static transfer switch, what we did is we implemented an algorithm called ATSM. ATSM stands for Automatic Transformer Switching Management, and it will limit the inrush current on any transfer on a PDU. So even if there is a PDU downstream of the static transfer switch with a transformer, the STS will very lightly slow down the transfer. We are speaking now about 10 milliseconds, 15 milliseconds, nothing more than a cycle, so nothing above 16 milliseconds. So the STS will ensure a transfer, still ITIC compliant, but reducing the inrush current up to nominal current. So at this moment, when we have ATSM on the right side, we can see the curve of the current downstream of the STS at the PDU level. And so the PDU will not generate any inrush when we implement our algorithm in the static transfer switch. It's very important to understand this ATSM feature in North America because we are working with PDUs 90–95% of the time in data center. So it's important to have this algorithm limiting any transfer on a PDU. High level of serviceability in the Socomec static transfer switch is thanks to the module design. So having this power module static transfer switch will help to isolate all of the boards. So here we have an example of a static transfer system powered by a Socomec static transfer switch module. So when we are on bypass in the static transfer switch system, we can access to the Socomec power module at any time, having this power module isolated completely from any voltage. We can, at this moment, do maintenance reports, get a maintenance report on the module and get access to all the data. And we can have maintainability features at this moment. So if we are in bypass, the power module is fully isolated. We can still access this power module being on normal mode without being in bypass. When we are on normal mode, we can do some hot swap maintenance being on the low energy area on the left side. So what can we do is, for example, we can do hot swap on the fans. So the fans are mounted on drawers. So even being on normal mode, we can remove a fan. There is full redundancy on the fans. So even if we remove one fan, the STS is still fully operating. Same hot swap can be on the power supply. So we can disconnect one power supply and do maintenance on the power supply. Again, we spoke about 3 redundant power supplies, so we can disconnect up to 2 power supply, having the power module fully operational. And what we can do as well is go in bypass mode, totally isolate the power module, and we can remove the power module from the static transfer switch system. So the Socomec power module is patented to be cold swappable. So when we are on bypass, we can remove the static transfer switch module can be on rails, and this rail can help to extract the power module. Only one person, we can do this extraction with only one maintenance technician. Another advantage is to do the maintenance outside of the static transfer switch system. So having all of the power supply, all of the microcontroller, all of the PCBAs, all of the SCR in this power module, we can have maintenance outside of the unit and work on any critical components being fully isolated outside of the cabinet. On top of that, the customer can purchase a spare module in order to have a factory testing module and bring it live in less than 30 minutes through the cold swap patented advantage. And so it's another level of maintainability, having some hot swap feature, cold swap feature. It's a very advanced design in order to increase the maintainability of the data center architecture. We are using the Socomec metering system in our static transfer switch. So we do have at Socomec some power quality meter that we are embedding in our system in order to do the waveform capture. It's important to know that the Socomec STS have waveform capture as standard in order to log the data and recreate the event in the future in order to analyze and understand why there was a transfer. So every time there is a transfer on the STS, the Socomec metering system will record the waveform capture, 50 millisecond window, in order to be able to analyze the data. So Socomec is providing static transfer switch power module in North America, and we are having a full range from 400 amp to 1200 amp, integrating them in system in order for the data center to have a very efficient and very resilient architecture using the Socomec static transfer switch. That's all for the presentation today. I want to thank you. Please be aware that Socomec is a technology innovator in data center. We are, of course, having the knowledge of static transfer switch, but also we are an actor for switching device, having fuse disconnect switches, automatic transfer switches, metering system, so that's all of the expertise we can bring for data center architecture. Today we had a focus on static transfer switch, but be aware that it's not the only technology that we have in North America. Thank you.
Thank you, Pierre, for that informative presentation. We'll now go through some questions you guys had throughout the presentation, but if you have any more, please ask them in the question and answer tab. So our first question for Pierre is, without ATSM, in case of transient, does it typically remain on the transformer primary or also on the secondary of the PDU?
So that's a good question. So the thing is, we must understand how the ATSM works. The ATSM is an algorithm understanding the behavior of the transformer. So what will happen when the ATSM is on? The transformer will not create at all the transient. So on the primary and on the secondary, there will not be any transient because the STS will prevent the transient to happen. If there was no ATSM, there would be a transient on the primary and on the secondary side of the transformer. So without ATSM, there could be a fault going up to the loads, and we can lose some loads. So it's very important to understand that we must use ATSM feature in a data center architecture having PDUs and STS.
Thank you, Pierre. Another question we have is, how long has Socomec been manufacturing STSs?
So Socomec has been manufacturing STS for 30 years. It came from the UPS technology. So Socomec has been manufacturing UPS for 50 years. And having this knowledge, Socomec had begun to manufacture static transfer switch for 30 years ago. And we are now at the 4th generation of static transfer switch. I just say that to show that we have expertise in static transfer switch. 4th generation, it means that we got a lot of feedback from customers. So it's something that we used this knowledge in order to increase the technology of the static transfer switch and have this expertise on our product.
Thank you. Another question we have is, what are the most popular STS models in the market in terms of current capacity?
So to speak about current capacity. So usually when we speak about STS, we speak about a package of STS and PDUs. So what we are seeing in the North American market is a combo of static transfer switch and PDU rated together. For example, we see a lot of 500 kVA PDU powered by a 600 amp static transfer switch, or 1 megawatt PDU powered by a 1200 amp static transfer switch. So at this moment, I would say today's rating which are the most popular in North America are 600 amp static transfer switch and 1200 amp static transfer switch.
Great. Another question we have is, how can a power module be serviced outside of a cabinet?
As we saw in the presentation, is the Socomec power module is cold swappable patented, meaning being on bypass on the system, we can remove the power module fully safe. And at this moment, there is two possibilities. The first possibility would be to bring a factory tested power module and bring it in the system. And so at this moment, it's very fast. We don't have even to do troubleshooting of the power module on site. We can ship a power module to a service center and service it. Or when we remove the power module, we can open this power module. Through the diagnosis, we would be able to identify which component had failed. If it's a PCBA, if it's a fan, if it's a power supply, if it's a SCR, we would be able to identify that, and fully out of the data center power system, we would be able to service the power module.
Great. And we have one more question in the chat. Is an external bypass necessary?
No. In static transfer switch, bypass are inside the system, meaning when we have a static transfer switch cabinet, and inside we use a static transfer switch from Socomec, the power module, there is an embedded bypass on the cabinet level, meaning for each source 1 and source 2, we have bypass 1 and bypass 2. So in order to service the component inside the static transfer switch system, we will put the unit in bypass from the internal bypass molded case switch, and we'll be able to isolate all of the control of the static transfer switch.
Thank you, Pierre. It looks like you've answered all of our questions today. If anyone has any questions after the webinar, feel free to email us at info.us@socomec.com, and we'll get back to you shortly with those. Thank you again for listening to us, and have a great rest of your day. Thank you, Pierre.
Thank you.